In 2D space, we typically describe lines in y equals mx plus b format or in point slope form. So do lines exist in 3D space? Well, of course they do. The issue, though, is that neither of the forms we learn in an algebra class are really that nice in terms of generalizing to 3D. So there's another format for lines in 2D that doesn't usually get covered because the two forms we have tend to be fairly convenient. But this other format for lines in 2D happens to generalize very nicely to 3D. So to lead up to this new way of looking at lines, let's think back to position vectors. Remember that a position vector is a vector that starts at the origin. So we can create a one-to-one correspondence or a bijection, or just a complete pairing up like a buddy system between the set of vectors and the set of points, right? The set of 2D vectors and the set of points in the plane. There's a complete connection. Each point in the plane corresponds to a different vector. For example, the vector 713 corresponds to the point 713. Technically, 713 in angle brackets is the vector, which starts at the point 0, 0 and ends at the point 713, while 713 in parentheses is just the point itself, as learned in algebra. However, in what we're about to do for a moment, we're going to pass back and forth between the vector and the point, and we will be very loose about which thing is which. And so we'll just kind of use this loose phrasing like the vector 713 corresponds to the point 713. Sorry for the misspelling. Okay, so to explore what's going on, let's define the vector r0 or r0 to be negative 3, 2, and the vector v to be 4, comma, negative 2. And I'd like to go through this computation. If t is the scalar 0, what vector we get here, right? So we've got a scalar t times a vector. So tv, scalar times vector, will end up being a vector, and then we do vector plus vector. So we'll go through the algebra, and then what we get is a vector, and then we'll talk about the corresponding point, which just basically means we take those angle brackets and make them round. So I won't show all the steps of the arithmetic, but this, of course, this one's nice, right? 0 times whatever, that part's going to be gone. So the corresponding point is negative 3, 2. If you plug in t is 1 instead, the corresponding point is 1, 0. If you plug in t is 2, the vector was 5, negative 2 in angle brackets, so the point is 5, negative 2 in parentheses. If t is a half, here's the point. If t is negative 1, then the point is negative 7, comma, 4. The thing to really dig into is what shape is formed by all of these points. And let's click on this. And I hope you see it's zooming very quickly, but this in red is just an individual point. And you can see kind of where this is. What shape is made by this? Actually, I have a little typo here, so let's fix that first. Right, so what shape is made by all the points in red? I mean, they're just sort of flashing really quick. Okay, so that's what's forming the shape of a line, of course, right? And yeah, that's what's down at the bottom of that slide. And so here's what's really going on. This is called the vector equation for a line. So this is different from y equals mx plus b. It's a vector-based format, and we are using this correspondence between points and vectors. So it looks like this. Vector r equals a fixed vector called r0 plus t, a scalar, times a vector called v. So r is a generic point or corresponding to a vector, and then r0 is a specific point corresponding to a vector. It's a point that's on the line, which is converted into vector format. T is a parameter. Think about the scalar parameter that's used in parametrization. And then vector v is a fixed vector. It's a vector that's parallel to the line. So what's going on in the example we just looked at, we can multiply in this t, do the scalar multiplication and do our vector addition and get a thing that looks like this. And so we could have written our earlier example, like this example written in this format, kind of more in this format as well. And I've just included the of t, and this is another form of writing the vector equation for the line. And here's another format. We can take this information and we're basically trying to say, we get this vector, but remember that we're saying that there's this correspondence between points and vectors. So instead, we could just say, how about the point where the x-coordinate is negative 3 plus 4t, and the point where the y-coordinate is 2 minus 2t. And this you may recognize as parametrization of a line. So here's another format. So from this parametrization That's a description of a line as well, and I hope this actually, if you really stop and think about it, justifies why what we have here worked in the first place. Another way you can look at this, here's a third format. Based on this parametric form, which is probably my favorite form, here's another version that the book author advocates for. I don't think we'll use it a whole lot, but it's just good to go over. Solve for t in each of these equations. Um, there we go. And then since t is equal to this fraction and t is equal to that fraction, you just set these equal. And this is what the book author calls the symmetric equation of a line. Okay, x plus 3 over 4 equals y minus 2 over negative 2. I don't think we'll use it a whole lot, but it's just good to have in mind. Just some reminders about parametrization, because this is parametrization as a concept is one of the most important things we need in the final chapter. So just a reminder that x equals cosine of t, y equals sine of t, t going from 0 to 2 pi describes a full circle. If we switch up the x formula by putting a 2 in front of the cosine of t, this should stretch only the x coordinate, but not the y coordinate. So you can think about what shape that makes, right? That should form an ellipse. Contrast this with x equals negative 3 plus 4t and y equals 2 minus 2t, which we had seen earlier. This is a line. Notice the absence of sines and cosines.